Many conversations about machine learning focus on the frontier, transformers, foundation models, the latest architecture that broke a benchmark. But most of the models making real decisions in the world are not those models. They're deciding who gets a loan, which transaction is fraud, which customer is about to leave, how much inventory to order. And the models doing that work are usually decision trees, random forests, gradient boosting, and support vector machines. Classical machine learning does not dominate production because it is old. It dominates because it works, it generalizes, and it is defensible when something goes wrong. This video covers the toolkit that actually runs most of the world. Some problems cannot be solved cleanly with linear models. Customer churn is a good example. Some customers remain loyal up to a certain usage threshold. Then the likelihood of churning rises sharply once they drop below it. Other patterns depend on interactions between features. Offering a discount might reduce churn among budget-conscious customers, but backfire among premium subscribers who value exclusivity. A linear model forces those dynamics into a straight line. It assigns the same weight to discount sensitivity regardless of the customer segment. The result is low accuracy and a false sense of confidence. This is exactly the class of problem that non-linear models were designed for. Problems where the decision boundary is not a line, and where the interactions between features matter as much as the features themselves. K-nearest neighbors makes predictions by finding the K-training examples closest to a new observation, and taking a majority vote among them. No explicit model is learned. The algorithm memorizes the training data and uses distance at prediction time. After training the K-nearest neighbors model, we evaluate its performance on the test set using a classification report. This report shows precision, recall, and F1 score for each class, along with overall accuracy. In this example, the model achieves an accuracy of about 83% on the test data. Precision tells us how often the model is correct when it predicts a class. Recall tells us how often the model correctly identifies all observations of a class. The F1 score balances precision and recall into a single metric. Notice that the performance is fairly balanced between the two classes, which tells us the model is not strongly biased toward one class over the other. This evaluation step is critical. Training a model is not the goal. Measuring how well it performs on new, unseen data is the goal. The choice of K controls model complexity. A very small K memorizes noise and produces highly irregular decision boundaries. A larger K produces smoother decision boundaries and better generalization. In practice, K is usually selected using cross-validation rather than guessing. The important point is that tuning is not cosmetic. It is what separates a model that learns structure from one that learns noise. Cross-validation gives us a measured way to choose K instead of guessing. This graph shows the average cross-validated accuracy for each value of K from 1 to 30. Each point represents how well the model performed, on average, across multiple validation folds for that specific value of K. In this example, the highest cross-validated accuracy occurs at K equals 23, which is why it is selected as the best value of K. That does not mean every nearby value is bad. In fact, several values in the low 20s perform similarly well. But K equals 23 produces the strongest average validation performance in this run, so it is the most defensible choice based on the evidence. This is the practical purpose of cross-validation. Compare candidate settings systematically, measure how they perform on held-out data, and choose the value that generalizes best according to the validation results. So, the takeaway from this graph is straightforward. K equals 23 delivered the best average validation accuracy, which is why it was selected instead of chosen by intuition alone. This plot shows the bias-variance trade-off in k nearest neighbors as k changes. When k is very small, the model closely follows the training data. Bias is low, but variance is high, which means the model is sensitive to noise and may overfit. When k is very large, the model averages over too many points. Variance is low, but bias is high, which means the model becomes too simple and may underfit. The optimal region is in the middle, where the total error curve reaches its minimum. This point represents the best balance between bias and variance, and in this example, it occurs around k approximately equals 23. This is sometimes called the elbow point, where increasing model complexity no longer improves performance and begins to increase error instead. A useful way to think about this is a real-world analogy. Imagine moving to a new city and trying to predict whether a restaurant is good by asking nearby people. If only one person is asked, the prediction depends entirely on that one opinion. That is like overfitting. If the entire city is asked, the answer becomes an average that may ignore local preferences. That is like underfitting. If a moderate number of nearby people is asked, the result balances local information with stability. That is the sweet spot. So tuning is not about making the model look better on paper. Tuning is about making the model work better in the real world. Decision trees take a different approach to classification than k nearest neighbors. Instead of measuring distance between observations, a decision tree learns a series of decision rules from the training data. In this example, a synthetic dataset is created with two features, and a decision tree classifier is trained on the training portion of the data. The tree learns by repeatedly splitting the data based on feature thresholds that best separate the classes. Each split divides the data into smaller and more homogeneous groups. The max_depth equals 3 parameter limits how deep the tree is allowed to grow. This is important because a fully grown tree can memorize the training data and overfit. By limiting the depth, the model is forced to learn broader patterns instead of memorizing individual observations. After the model is trained, it is used to make predictions on the test set, which allows us to evaluate how well the tree generalizes to new, unseen data. After making predictions on the test set, the next step is to evaluate how well the decision tree performed. This slide shows the classification report for the decision tree model. While accuracy tells us the overall percentage of correct predictions, the classification report provides a more detailed breakdown of model performance. Precision measures how often the model is correct when it predicts a class. Recall measures how often the model correctly identifies all observations of a class. And the F1 score balances precision and recall into a single metric. Together, these metrics provide a more complete understanding of model performance than accuracy alone, showing not just how often the model is correct, but how it makes mistakes across different classes. Next, a confusion matrix is generated. The confusion matrix shows how many observations were correctly classified and where the model made mistakes. The diagonal values represent correct predictions, while the off-diagonal values represent misclassifications. Finally, the decision tree itself is visualized. The tree diagram shows the sequence of feature-based splits the model learned from the training data. Each internal node represents a decision rule based on a feature threshold, and each leaf node represents a final class prediction. This visualization is one of the major advantages of decision trees. The model is transparent. A prediction can be explained by tracing the path from the root of the tree to a leaf node and following the decision rules step by step. However, this also highlights the main risk of decision trees. If the tree is allowed to grow too deep, it will begin to memorize the training data instead of learning general patterns. That is why parameters like maximum depth are used to control model complexity and improve generalization. Random forests address the single tree's central weakness, variance, by building many trees and combining their predictions. Each tree trains on a different bootstrap sample of the data. At every split, only a random subset of features is considered. This double layer of randomness decorrelates the trees, so their errors do not all point in the same direction. When predictions are averaged, the individual errors tend to cancel. The result is a model substantially more stable than any single tree, with better generalization and still capable of producing feature importance scores that identify which variables drove the predictions. In most applied settings, a well-tuned random forest is the benchmark every other model has to beat. If you cannot outperform it, you have not earned the complexity of something harder to explain. When multiple algorithms are run head-to-head on the same structured dataset, the results often surprise people. Logistic regression, k-nearest neighbors, decision tree, random forest, and support vector machine, all trained on the same data. The result? Every model clusters within a few percentage points of every other. The sophisticated nonlinear models do not dramatically outperform the regularized linear baseline. And in many cases, the simplest model sits at the top. This is a lesson many practitioners learn the hard way. For structured, tabular data with moderate sample sizes, no single algorithm has a decisive edge. The right question is never which algorithm is most impressive. It is which algorithm fits the problem, and which one you can actually explain when something goes wrong. Ensemble learning extends the classical toolkit by combining multiple models to achieve better performance than any single model alone. 4 strategies matter in practice. Bagging trains models independently on bootstrap samples and averages their predictions, reducing variance. Boosting trains models sequentially. Each new model corrects the errors of the ensemble so far, reducing bias through iterative refinement. Gradient boosting is the most widely used version of this idea. Voting combines diverse models by averaging their probability estimates. Soft voting works best when the base models are well calibrated and their errors are uncorrelated. Stacking goes one step further, training a meta model to learn the optimal way to weight the predictions of the base models, treating those predictions as input features for a second-level learner. To ground this in a real example, the Banknote authentication dataset from OpenML is used. It contains just over 1,300 observations, with 4 numerical features derived from banknote images, and the task is to classify each note as authentic or counterfeit. The same set of models is trained under identical conditions: decision tree, random forest, gradient boosting, soft voting, and stacking, using a consistent pre-processing pipeline and controlled data splits. When the results are evaluated, the pattern is immediate. On both the validation and test sets, the ensemble methods converge to nearly identical performance. Accuracy is approximately 99.6%, with AUC and average precision effectively at 1.0 across multiple models. Even the single decision tree performs strongly, only slightly behind the ensembles. This is the point. The dataset is clean. The signal is strong. The classes are well separated. So multiple algorithms arrive at the same answer. The takeaway is not which model won. The takeaway is that the problem was already solved by the features. When the signal is strong, the algorithm matters less. When the signal is weak, that is when model choice begins to matter. As you move from decision trees to forests to stacking ensembles, performance generally improves. So does opacity. A single decision tree can be visualized, traced, and explained. A random forest with hundreds of trees cannot be meaningfully interpreted by a human. A stacking ensemble adds another layer of abstraction on top. In some industries, that trade-off matters. If a model is used to approve loans, set insurance rates, or make hiring decisions, stakeholders may have a legal right to an explanation for the decision. So there is a practical principle that shows up again and again in applied machine learning. Do not default to the most complex model. Start with the simplest model that can solve the problem. Only add complexity when the data demands it and the deployment context allows it. Chapters 4 and 13 of my book Applied Machine Learning, Concepts, Tools, and Case Studies walk through every model covered in this video with working code, customer churn prediction with the full 5-model comparison, and Banknote authentication with the complete ensemble benchmarks. The bias variance trade-off, regularization mechanics, ensemble strategies, and the accuracy interpretability tension are all worked through concretely. If this is how you want to learn, the link to my book is in the description. Once you have a model, classical or otherwise, the next critical question is whether it is actually good. Most reported model metrics are more optimistic than real-world performance warrants. Video 5 is about evaluation. Where the numbers lie, why they lie, and what rigorous validation actually looks like in production. The best model for a problem is not the most sophisticated one. It is the simplest one that is good enough for the context in which it will be used. Start with classical machine learning. Add complexity only when the data demands it and when the deployment environment can support it. That is how machine learning actually works in practice. See you in the next video.